Hello, and welcome to Calm Science Nights. I'm so glad you're here with me tonight. Before we begin our peaceful journey through our home galaxy, if you find comfort in drifting off to the soothing rhythm of cosmic wonder, please consider subscribing to the channel. It helps us create more of these tranquil explorations together. Now, settle into your most comfortable position. Let the weight of the day lift from your shoulders. Tonight, we're going to take a gentle voyage through the Milky Way, the vast island of stars that is our cosmic home. We'll trace the story of how humanity came to understand this magnificent spiral of light, from ancient mythologies to modern discoveries, each fact a stepping stone in our journey to comprehend the galaxy we inhabit. There's something deeply restful about contemplating the Milky Way, that soft band of light stretching across the night sky, a river of stars so distant and numerous that they blend together into a luminous path. Over the next 100 facts, we'll walk this peaceful path together, discovering what that band of light truly is, how it formed, what lies at its center, and where we fit within its vast spiral arms. There's no need to remember everything tonight. In fact, there's no need to stay awake at all. Let these words wash over you like gentle waves, each fact a soft ripple in the stream of discovery, carrying you peacefully towards sleep. Just allow the story to unfold at its own unhurried pace, the way the galaxy itself turns, slowly, gracefully, completing one rotation every 225 million years. Close your eyes now, and imagine yourself in a place far from city lights, standing beneath a truly dark sky on a clear moonless night. Above you, stretching from horizon to horizon like a glowing river across the heavens, is the Milky Way. Our story begins here, with this beautiful band of light that has captivated every human culture that has ever looked up at the night sky. The ancient Greeks saw this luminous path and called it galaxies kyklos, the Milky Circle, because it resembled a stream of spilled milk across the darkness. Their mythology told that the goddess Hera was nursing the infant Heracles when he bit down too hard, and she pulled away, spraying milk across the sky. The Romans adopted this story and called it Via Lactea, the Milky Road or Milky Way, the name we still use today. But the Greeks and Romans were not alone in their wonder. Nearly every culture on Earth has myths about this celestial river. The ancient Chinese called it the Silver River and told stories of a celestial weaver separated from her cowherd love by this river of stars. The Hindus saw it as the dolphin of the god Vishnu swimming through the cosmic ocean. Aboriginal Australian peoples saw it as a river where the souls of the dead traveled to the afterlife. The Maya saw it as the road to Xibalba, the underworld. Across all of human history, across all cultures and continents, people looked up and saw the Milky Way and knew they were seeing something profound, something that connected them to the cosmos. But what was this band of light? For thousands of years, no one could say with certainty. Aristotle, the great Greek philosopher, believed the Milky Way was a phenomenon in Earth's atmosphere, perhaps a kind of fire or burning vapor in the upper air. He thought it was closer to Earth than the Moon, a terrestrial rather than celestial phenomenon. Others thought it might be a cloud of some kind, or perhaps a seam where the crystal spheres of the heavens joined together. The truth remained hidden, beyond the reach of human eyes unaided by instruments. The first person to see what the Milky Way truly was, or at least to begin to see, was Galileo Galilei. In 1609, when Galileo turned his newly improved telescope toward the heavens and looked at that pale band of light, he saw something that astonished him. The Milky Way, he discovered, was not a cloud or a vapor or atmospheric fire. It was made of stars, countless individual stars, so many and so distant that to the naked eye they blended together into a continuous glow. The galaxy, Galileo wrote, is nothing else but a mass of innumerable stars planted together in clusters. This was a revolutionary discovery. It meant that the Milky Way was not a nearby atmospheric phenomenon but something truly celestial, a vast collection of stars extending far into space. Each tiny point of light that made up the milky glow was a sun, perhaps like our own, shining across unimaginable distances. The implications were staggering. If the Milky Way contained so many stars, how large must it be? How far away were these stars? And what was the structure of this vast stellar assembly? These questions would occupy astronomers for the next several centuries. In the 1700s, the philosopher Immanuel Kant proposed a remarkable idea. He suggested that the Milky Way was a vast, flattened system of stars, what he called an island universe, and that our sun was just one star among countless others, all bound together by gravity into a disc-shaped structure. Kant even speculated that the faint nebulae visible in telescopes might be other, distant island universes, other Milky Ways far beyond our own. It was a brilliant insight, though Kant had no way to prove it. The person who would first attempt to map the Milky Way's structure was William Herschel, the same astronomer who had discovered Uranus. In the late 1700s and early 1800s, Herschel and his sister Caroline embarked on an ambitious project. They would count stars in different directions across the sky to determine the shape and extent of the Milky Way. Herschel reasoned that if he looked in a direction where the Milky Way extended far, he would see more stars. If he looked in a direction where it was shallow, he would see fewer stars. By systematically counting stars in hundreds of different directions, he could map out the galaxy's shape. The results of Herschel's star counts suggested that the Milky Way was indeed flattened, roughly disc-shaped, and that the Sun was located near the center of this disk. The Milky Way, according to Herschel's model, was like a lens or a grindstone, thicker in the middle and thinner at the edges, and we were somewhere near the middle looking out in all directions. When we looked toward the plane of the disk, we saw the characteristic band of the Milky Way because we were looking through the greatest thickness of stars. When we looked perpendicular to the disk, above or below the plane, we saw fewer stars because we were looking through the thinner dimension. Herschel's model was groundbreaking, the first serious attempt to map our galaxy's structure. But it was also wrong in important ways, as later astronomers would discover. Herschel had assumed that all stars were equally bright intrinsically, so that a fainter star was simply farther away than a bright one. He also couldn't account for something called interstellar extinction, the dimming of starlight by dust in space. These factors led him to underestimate the true size of the Milky Way and to incorrectly place the Sun near its center. The truth was far stranger and more wonderful than Herschel could have imagined from his star counts alone. As the 19th century progressed, telescopes grew larger and more powerful, revealing more details about the Milky Way and the mysterious nebulae scattered across the night sky. Some nebulae were clearly clouds of gas, glowing or reflecting the light of nearby stars. But others were different. They appeared as faint, fuzzy patches of light with a spiral or elliptical structure. These spiral nebulae were particularly puzzling. Were they clouds of gas within our Milky Way, Or were they something else entirely? This question, whether spiral nebulae were part of the Milky Way or separate galaxies beyond it, became one of the most heated debates in early 20th century astronomy. Some astronomers, measuring the rotation of spiral nebulae and the speeds of material within them, argued that if these objects were within the Milky Way, the speeds implied would be impossibly high. They must be separate systems, island universes as Kahn had speculated, lying far beyond our galaxy. Other astronomers disagreed, arguing that the evidence was inconclusive and that spiral nebulae could still be part of our Milky Way. The debate came to a head on April 26, 1920, in what became known as the Great Debate, held at the Smithsonian Museum of Natural History in Washington, D.C. Two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views about the nature of the Milky Way and the spiral nebulae. Shapley argued that the Milky Way was enormous, much larger than previously thought, and that spiral nebulae were relatively small objects within it. Curtis argued that the Milky Way was smaller and that spiral nebulae were separate galaxies comparable in size to our own, scattered throughout a much larger universe. And so our journey has begun with the ancient observation of the Milky Way, that luminous band of light stretching across the night sky that captivated every human culture. The ancient Greeks called it galaxias kyklos, the Milky Circle, because it resembled spilled milk across darkness. Mythology told that goddess Hera nursing infant Heracles pulled away when he bit too hard, spraying milk across sky. Romans called it Via Lactea, the Milky Road or Milky Way, the name we still use today. We learn nearly every Earth culture has myths about this celestial river. Ancient Chinese called it Silver River, celestial weavers separated from cowherd love by Star River. Hindus saw it as Vishnu's dolphin swimming through cosmic ocean. Aboriginal Australian peoples saw it as river where dead souls traveled to afterlife. Maya saw it as road to Xibalba, underworld. Across all human history, all cultures and continents, people looked up and saw the Milky Way knowing they were seeing something profound connecting them to cosmos. We discovered for thousands of years no one could say with certainty what this band of light was. Aristotle believed Milky Way was Earth atmosphere phenomenon, perhaps upper air fire or burning vapor, thought it was closer to Earth than Moon, terrestrial rather than celestial phenomenon. Others thought it might be cloud or perhaps seen where heaven's crystal spheres joined together. Truth remained hidden beyond reach of unaided human eyes. We met Galileo Galilei, who in 1609 was first person to see what Milky Way truly was. When Galileo turned his newly improved telescope toward that pale light band, saw something astonishing. Milky Way was not cloud or vapor or atmospheric fire but made of stars, countless individual stars, so many and distant that to naked eye they blended together into continuous glow. The galaxy, Galileo wrote, is nothing else but a mass of innumerable stars planted together in clusters. We found this was revolutionary discovery, meant Milky Way was not nearby atmospheric phenomenon but truly celestial, vast star collection extending far into space. Each tiny point of light making up Milky Glow was a sun perhaps like our own shining across unimaginable distances, implications staggering. If Milky Way contains so many stars, how large must it be? How far away were these stars? What was this vast stellar assembly structure? We learned in 1700s philosopher Immanuel Kant proposed remarkable idea, suggested Milky Way was vast flattened star system, what he called island universe, and our Sun was just one star among countless others, all bound together by gravity into disk-shaped structure. Kahn even speculated faint telescopic nebulae might be other distant island universes, other Milky Ways far beyond our own. Brilliant insight, though Kahn had no way to prove it. We discovered William Herschel, same astronomer who discovered Uranus, in late 1700s and early 1800s, was first person to attempt mapping Milky Way's structure. Herschel and sister Caroline embarked on ambitious project, count stars in different sky directions to determine Milky Way's shape and extent. Herschel reasoned if he looked in direction where Milky Way extended far would see more stars, if looked where it was shallow would see fewer stars. By systematically counting stars in hundreds of different directions could map out galaxy shape. We found Herschel's star count results suggested Milky Way was indeed flattened, roughly disc-shaped, and Sun was located near this disk's center. According to Herschel's model, Milky Way was like lens or grindstone, thicker in middle, thinner at edges, and we were somewhere near middle looking out in all directions. When looked toward disk plane saw characteristic Milky Way band because looking through greatest star thickness, when looked perpendicular to disk, above or below plane, saw fewer stars because looking through thinner dimension. We learned Herschel's model was groundbreaking, first serious attempt to map our galaxy's structure, but also wrong in important ways later astronomers would discover. Herschel assumed all stars equally bright intrinsically, so fainter stars simply farther away than bright one, also couldn't account for interstellar extinction, starlight dimming by space dust. These factors led him to underestimate Milky Way's true size and incorrectly place Sun near its center. Truth was far stranger and more wonderful than Herschel could imagine from star counts alone. We discovered as 19th century progressed, telescopes grew larger and more powerful, revealing more Milky Way details and mysterious nebulae scattered across night sky. Some nebulae clearly gas clouds glowing or reflecting nearby starlight, but others different, appeared as faint fuzzy light patches with spiral or elliptical structure. These spiral nebulae particularly puzzling. Were they gas clouds within our Milky Way or something else entirely? We found this question, whether spiral nebulae were part of Milky Way or separate galaxies beyond it, became one of early 20th century astronomy's most heated debates. Some astronomers measuring spiral nebulae rotation and internal material speeds argued if these objects were within Milky Way, implied speeds would be impossibly high, must be separate systems, island universes as Kant speculated, lying far beyond our galaxy. Other astronomers disagreed, arguing evidence was inconclusive and spiral nebulae could still be part of our Milky Way. We learned debate came to head April 26, 1920 in what became known as Great Debate, held at Smithsonian Museum of Natural History in Washington, D.C. Two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views about Milky Way nature and spiral nebulae. Shapley argued Milky Way was enormous, much larger than previously thought, and spiral nebulae were relatively small objects within it. Curtis argued Milky Way was smaller and spiral nebulae were separate galaxies comparable in size to our own scattered throughout much larger universe. Each fact a gentle step in understanding slow emergence, the gradual realization that the pale band of light overhead is not a celestial river but a view through our own galaxy's disk, a glimpse of hundreds of billions of distant suns all wheeling together in cosmic motion. From ancient myths to Galileo's revelation, from Herschel's star counts to the Great Debate, each mind building on the last, slowly assembling the truth. Feel yourself in that gentle awakening now, standing with those ancient astronomers looking up at the Milky Way and wondering what it is, what it means, where we fit in its vast structure. There's nothing to solve tonight, nothing to grasp. Just rest in the slow unfolding of discovery, in the peaceful rhythm of minds opening to truth, generation after generation, slowly, beautifully, like the galaxy itself turning through the darkness of space. Let the Milky Way carry you now, that ancient river of light wheeling overhead, containing our sun and our earth and everything we've ever known, turning slowly through the cosmos, peaceful and unhurried, drifting gently towards sleep. As we continue our peaceful journey through the story of the Milky Way, we move forward from the great debate into a time when new technologies and new ways of seeing would finally reveal the true nature of our galaxy, its size, its structure, and our sun's humble position within it. The answers, when they came, would be both humbling and awe-inspiring, showing us that we live in a galaxy far grander than anyone had imagined. The great debate of 1920 ended without a clear victor. Both Shapley and Curtis had compelling arguments, but neither had definitive proof. The question of the Milky Way's size and the nature of spiral nebulae would remain unresolved for several more years. But the tools needed to answer these questions were already being developed. The key would come not from simply looking at stars and nebulae, but from understanding their light in a deeper way, from measuring not just their brightness and position, but their distance. The breakthrough came from studying a special type of star called a Cepheid variable. These are stars whose brightness varies in a regular, predictable way, pulsing brighter and dimmer over periods ranging from days to months. In 1908, Henrietta Swan Leavitt, working at Harvard College Observatory, made a crucial discovery while studying Cepheid variables in the Small Magellanic Cloud, a small companion galaxy to the Milky Way visible from the southern hemisphere. Leavitt noticed that the brighter Cepheid variables had longer periods. They took more time to complete their cycle of brightening and dimming. This relationship between a Cepheid's intrinsic brightness and its period was profound, because it meant that Cepheids could be used as standard candles for measuring cosmic distances. If you observed a Cepheid variable and measured its period, you could calculate how bright it truly was. Then, by comparing that intrinsic brightness to how bright it appeared from Earth, you could determine how far away it was. The dimmer it appeared compared to its true brightness, the farther away it must be. This simple relationship would revolutionize astronomy, giving scientists a way to measure distances across the cosmos. In the early 1920s, a young astronomer named Edwin Hubble began using the most powerful telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson in California, to search for Cepheid variables in spiral nebulae. The telescope was large enough and sensitive enough to detect individual stars in these faint, fuzzy patches. In 1923, Hubble found what he was looking for: Cepheid variables in the Andromeda Nebula, one of the brightest and most prominent spiral nebulae in the sky. By measuring the periods of these Cepheids and using Leavitt's period luminosity relationship, Hubble calculated their distance. The result was astonishing. The Andromeda Nebula was approximately 900,000 light-years away, far beyond even the most generous estimates of the Milky Way's size. This meant that Andromeda was not a nebula within our galaxy but a separate galaxy entirely, an island universe containing billions of stars, comparable to the Milky Way itself. Curtis had been right. The spiral nebulae were separate galaxies, scattered throughout a universe far larger than anyone had dared imagine. Hubble's discovery, announced in 1924, fundamentally changed our understanding of the cosmos. The Milky Way was not the entire universe, as many had thought, but just one galaxy among countless others. The universe suddenly became vastly larger, populated with billions of galaxies, each containing billions of stars. Our cosmic address expanded. We lived on Earth, orbiting the Sun, which was one star among hundreds of billions in the Milky Way galaxy, which was itself just one galaxy among billions in the observable universe. But what about the other part of the great debate, the size of the Milky Way itself? Here, ironically, Shapley had been right, though his reasoning was partially flawed. Shapley's estimate of the Milky Way's size came from studying globular clusters, dense, spherical collections of hundreds of thousands of stars that orbit in a halo around the galaxy. By mapping the distribution of these globular clusters, Shapley found that they formed a roughly spherical distribution centered on a point in the constellation Sagittarius, about 30,000 light-years from the Sun. Shapley reasoned that the globular clusters must be centered on the true center of the Milky Way, and that therefore the Sun was not at the galaxy's center but out in the suburbs, roughly 2/3 of the way from the center to the edge. This was a Copernican scale revolution in perspective. Just as Copernicus had dethroned Earth from the center of the solar system, Shapley had now dethroned the Sun from the center of the galaxy. We were not in a privileged central position but rather in the galactic outskirts, one ordinary star among hundreds of billions, located in an unremarkable region of the Milky Way. Shapley's estimate of the Sun's distance from the galactic center was too large. He calculated about 50,000 light-years when the actual distance is closer to 26,000 light-years, but he had the essential picture correct. The Milky Way was enormous, far larger than Herschel had thought, and the Sun was not centrally located. The reason Herschel had been wrong was interstellar dust. Between the stars, especially in the plane of the Milky Way, there are clouds of dust that absorb and scatter starlight, making distant stars appear dimmer than they truly are. Herschel, not knowing about this dust, had interpreted the apparent thinning of stars in distant directions as the edge of the galaxy, when in fact he was simply seeing the dimming effect of dust. The Milky Way extended far beyond what he could see. As telescopes improved and astronomers mapped more of the Milky Way's structure through the 1930s and 1940s, a clearer picture emerged. The Milky Way is a spiral galaxy, similar to Andromeda, with a central bulge of older stars surrounded by a flat disk containing spiral arms. The disk is about 100,000 light-years in diameter, so large that light, traveling at 186,000 miles per second, takes 100,000 years to cross from one side to the other. The disk is relatively thin, only about 1,000 light-years thick in most places, making the Milky Way shaped somewhat like a dinner plate or a vinyl record. Our Sun resides in one of the spiral arms of this disk, in a minor arm called the Orion Arm or Orion Spur, positioned between two major spiral arms, the Sagittarius Arm and the Perseus Arm. We're located about 26,000 light-years from the galactic center, roughly halfway out to the visible edge of the disk. From our vantage point within the disk, when we look toward the constellation Sagittarius, we're looking toward the galactic center, and the Milky Way appears brightest and most densely packed with stars. When we look in the opposite direction, toward the constellation Auriga, We're looking toward the outer edge of the galaxy, and the Milky Way appears fainter and less dense. Understanding the Milky Way's spiral structure was challenging because we're embedded within it, trying to map a structure from the inside. It's like trying to draw a map of a forest while standing in the middle of it. You can see the trees immediately around you, but the overall pattern is hard to discern. Astronomers had to use clever techniques, mapping the distribution of young, hot stars and glowing hydrogen gas clouds that trace out the spiral arms, and later using radio telescopes to detect the radio emission from hydrogen gas throughout the galaxy, which can penetrate the obscuring dust that blocks visible light. And so we learned the Great Debate of 1920 ended without clear victor. Both Shapley and Curtis had compelling arguments, but neither had definitive proof. Question of Milky Way's size and spiral nebulae nature would remain unresolved for several more years, but tools needed to answer were already being developed. Key would come not from simply looking at stars and nebulae but from understanding their light in deeper way, measuring not just brightness and position but their distance. We discovered breakthrough came from studying Cepheid variables, stars whose brightness varies in regular predictable way, pulsing brighter and dimmer over periods ranging from days to months. In 1908, Henrietta Swan Leavitt, working at Harvard College Observatory, made crucial discovery while studying Cepheid variables in Small Magellanic Cloud, small Milky Way companion galaxy visible from southern hemisphere. Leavitt noticed brighter Cepheid variables had longer periods, took more time to complete brightening and dimming cycle. We found this relationship between Cepheids' intrinsic brightness and its period was profound because meant Cepheids could be used as standard candles for measuring cosmic distances. If you observed Cepheid variable and measured its period, could calculate how bright it truly was, then comparing that intrinsic brightness to how bright it appeared from Earth could determine how far away it was. Dimmer it appeared compared to true brightness, farther away it must be. This simple relationship would revolutionize astronomy, giving scientists a way to measure distances across cosmos. We met Edwin Hubble, who in early 1920s began using world's most powerful telescope at time, 100-inch Hooker telescope on Mount Wilson in California, to search for Cepheid variables and spiral nebulae. Telescope large enough and sensitive enough to detect individual stars in these faint fuzzy patches. In 1923, Hubble found what he was looking for: Cepheid variables in Andromeda Nebula, one of brightest and most prominent spiral nebulae in sky. We learned by measuring these Cepheids periods and using Leavitt's period luminosity relationship, Hubble calculated their distance. Result astonishing: Andromeda Nebula approximately 900,000 light-years away, far beyond even most generous Milky Way size estimates. This meant Andromeda was not nebula within our galaxy but separate galaxy entirely, island universe containing billions of stars comparable to Milky Way itself. Curtis had been right. Spiral nebulae were separate galaxies scattered throughout universe far larger than anyone had dared imagine. We discovered Hubble's discovery, announced 1924, fundamentally changed cosmos understanding. Milky Way was not entire universe as many thought, but just one galaxy among countless others. Universe suddenly became vastly larger, populated with billions of galaxies, each containing billions of stars. Our cosmic address expanded. We lived on Earth orbiting Sun, which was one star among hundreds of billions in Milky Way galaxy, which itself was just one galaxy among billions in observable universe. We found what about Great Debate's other part, Milky Way's size itself? Here ironically Shapley had been right, though reasoning partially flawed. Shapley's Milky Way-sized estimate came from studying globular clusters, dense spherical collections of hundreds of thousands of stars orbiting in halo around galaxy. By mapping globular cluster distribution, Shapley found they formed roughly spherical distributions centered on point in Sagittarius constellation about 30,000 light-years from Sun. We learned Shapley reasoned globular clusters must be centered on Milky Way's true center, therefore Sun was not at galaxy's center but out in suburbs roughly 2/3 of way from center to edge. This was Copernican scale perspective revolution. Just as Copernicus dethroned Earth from solar system center, Shapley now dethroned Sun from galaxy center. We were not in privileged central position but rather in galactic outskirts, one ordinary star among hundreds of billions located in unremarkable Milky Way region. We discovered Shapley's estimate of Sun's galactic center distance was too large, calculated about 50,000 light-years when actual distance closer to 26,000 light-years, but had essential picture correct. Milky Way was enormous, far larger than Herschel thought, and Sun was not centrally located. Reason Herschel was wrong. Interstellar dust, between stars especially in Milky Way plane, are dust clouds that absorb and scatter starlight, making distant stars appear dimmer than truly are. Herschel, not knowing about dust, interpreted apparent distant direction star thinning as galaxy edge when actually seeing dust dimming effect. Milky Way extended far beyond what he could see. We found as telescopes improved and astronomers mapped more Milky Way structure through 1930s to 1940s, clearer picture emerged. Milky Way is spiral galaxy similar to Andromeda with central older star bulge surrounded by flat disk containing spiral arms. Disk about 100,000 light-years diameter, so large that light traveling 186,000 miles per second takes 100,000 years to cross from one side to other. Disk relatively thin, only about 1,000 light-years thick in most places, making Milky Way shaped somewhat like dinner plate or vinyl record. We learned our Sun resides in one of disk's spiral arms, a minor arm called Orion Arm or Orion Spur, positioned between two major spiral arms, Sagittarius Arm and Perseus Arm. We're located about 26,000 light-years from galactic center, roughly halfway out to disk's visible edge. From our vantage point within disk, when we look towards Sagittarius constellation, we're looking toward galactic center and Milky Way appears brightest and most densely star-packed. When we look in opposite direction toward Auriga constellation, we're looking toward galaxy outer edge and Milky Way appears fainter and less dense. We discovered understanding Milky Way's spiral structure was challenging because we're embedded within it, trying to map structure from inside, like trying to draw a forest map while standing in middle of it. Can see trees immediately around you but overall pattern hard to discern. Astronomers had to use clever techniques, mapping young hot star distribution and glowing hydrogen gas clouds tracing spiral arms, later using radio telescopes to detect hydrogen gas radio emission throughout galaxy which can penetrate obscuring dust blocking visible light. Each fact a gentle step in understanding's deepening, the gradual realization that our Sun is not special, not central, but one ordinary star in the galactic suburbs, in a minor spiral arm of a galaxy that is itself just one among billions. From Leavitt's Cepheids to Hubble's distance measurements, from Shapley's globular clusters to the mapping of spiral arms, each discovery pushing us further from cosmic centrality, yet connecting us more deeply to the vast structure we inhabit. Rest in this cosmic humility now, this recognition that we are not at the center but in the outskirts, not privileged but typical, one small world orbiting one ordinary star in the quiet suburbs of a vast spiral galaxy. There's profound peace in this, in being part of something so much larger than ourselves, in belonging to this magnificent structure wheeling through space. Let yourself drift with the Milky Way's slow rotation, our Sun and our Earth carried along in the galactic current, orbiting the distant center every 225 million years, peaceful and unhurried, carried gently towards sleep. As we continue our peaceful journey through the story of the Milky Way, we move deeper into understanding not just the structure of our galaxy but what lies at its heart, how it moves, and what it's made of. The discoveries waiting in the decades following Hubble's revelations would reveal that the Milky Way is far stranger and more dynamic than a simple spiral of stars. It's a complex, evolving system with secrets hiding in its center and mysteries woven throughout its vast expanse. By the 1940s and 1950s, astronomers had established the basic structure of the Milky Way, a spiral galaxy with our Sun positioned in the disk, far from the center. But a profound question remained: what was at the center itself? The galactic core, located in the direction of Sagittarius, was hidden behind vast clouds of interstellar dust that blocked visible light. Looking toward the galactic center with an optical telescope was like trying to see through a thick fog. The dust absorbed and scattered the light from distant stars, leaving the heart of our galaxy shrouded in darkness. The breakthrough came with the development of radio astronomy. Radio waves, unlike visible light, can pass through interstellar dust almost unimpeded. In the 1950s and 1960s, astronomers using radio telescopes began to map the galactic center and discovered something extraordinary. There was an intense source of radio emission right at the center of the Milky Way, a compact region that seemed to mark the exact gravitational heart of the galaxy. This source was named Sagittarius A, SGRA for short, and it would become one of the most studied objects in all of astronomy. As radio astronomy techniques improved, astronomers refined their observations of SGRA and discovered that it actually consisted of several components. The most interesting was a very compact, bright radio source they called Sagittarius A*, pronounced Sagittarius A star. This tiny region, no larger than the orbit of Mercury, was emitting tremendous amounts of energy. What could possibly be producing such intense radiation from such a small space? The answer, astronomers began to suspect, was something that had been predicted by Einstein's theory of general relativity but never definitively observed: a black hole. By the 1990s and 2000s, astronomers had developed powerful infrared telescopes that, like radio telescopes, could peer through the dust to see the galactic center. Using these instruments, they began tracking the motions of individual stars orbiting very close to SGRA star. What they found was astonishing. These stars were moving at incredible speeds, thousands of kilometers per second, whipping around SGRA* in tight elliptical orbits. One star, designated S2, completes a full orbit around SGRA* in just 16 years, despite the fact that its orbit takes it billions of miles from the center. By applying Newton's and Einstein's laws of gravity to these stellar orbits, astronomers could calculate the mass of whatever object was at the center pulling on these stars. The result was staggering. Sagittarius A* contains approximately 4 million times the mass of our Sun, all compressed into a region smaller than the orbit of Mercury. There was only one explanation that could account for so much mass in such a small space: Sagittarius A** is a supermassive black hole, and it sits at the very center of our Milky Way galaxy. This discovery revealed that our galaxy has a monster lurking at its heart, a black hole so massive that if it were active and feeding on nearby matter, it would shine brighter than billions of stars combined. Fortunately for us, SGRA* is currently relatively quiet, not actively consuming large amounts of material, so it doesn't blaze with the intense radiation that characterizes active galactic nuclei in other galaxies. But it's there, an invisible gravitational anchor holding the central region of the galaxy in its grip, a reminder that even the most beautiful cosmic structures can harbor violent, extreme objects at their cores. The presence of this supermassive black hole raised new questions. How did it form? Was it there from the very beginning of the galaxy's history, or did it grow over time? And perhaps most intriguingly, nearly every large galaxy astronomers observe seems to have a supermassive black hole at its center. Our neighboring galaxy, Andromeda, has one too, even more massive than ours, perhaps 100 million times the Sun's mass. This suggested a deep connection between galaxies and their central black holes, a relationship that astronomers are still working to understand fully. While astronomers were uncovering the secrets of the galactic center, others were studying how the Milky Way moves. We've mentioned that the Sun orbits the galactic center, but what exactly does that motion look like? Our Sun, along with all the other stars in our neighborhood of the galaxy, is traveling through space at about 514,000 miles per hour, roughly 230 kilometers per second, in a roughly circular orbit around the galactic center. At this speed, it takes the Sun approximately 225 to 250 million years to complete one full orbit, a period sometimes called a galactic year or cosmic year. This means that since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. The last time the Sun was at this point in its orbit, one cosmic year ago, about 225 million years ago, dinosaurs had just begun to appear on Earth. The time before that, about 450 million years ago, the first fish were evolving in Earth's oceans. Every point in Earth's history, every moment of the evolution of life, has occurred during the Sun's slow patient journey around the Milky Way, riding the galactic currents through space. But this orbital motion revealed another mystery, one that would have profound implications for our understanding of the universe. When astronomers measured the orbital speeds of stars and gas at different distances from the galactic center, they found something unexpected, the same puzzle we encountered when discussing why everything spins. Based on the visible matter in the galaxy, the stars and glowing gas we can see, stars in the outer regions of the galaxy should be orbiting more slowly than those closer to the center, just as outer planets in the solar system orbit more slowly than inner planets. But that's not what they found. Instead, the rotation curve of the Milky Way was flat. Stars in the outer reaches of the galaxy were moving just as fast as those closer in, sometimes even faster. This meant there wasn't enough visible matter to account for the gravitational pull needed to keep these stars in their orbits. They should be flying off into intergalactic space, flung away by their own speed. Yet they weren't. Something was holding the galaxy together, providing the extra gravity needed to keep the outer stars bound to the galaxy. This something was dark matter, the mysterious invisible substance that doesn't emit, absorb, or reflect light, but whose gravitational influence can be detected through its effects on visible matter. The Milky Way, like all galaxies, is embedded in a vast halo of dark matter that extends far beyond the visible disk of stars. This dark matter halo provides the gravitational scaffolding that holds the galaxy together and explains the flat rotation curve. In fact, the dark matter halo is far more massive than all the visible matter in the galaxy combined. The stars, gas, and dust we can see, everything that makes the Milky Way visible and beautiful, represents only about 10 to 15% of the galaxy's total mass. The rest, about 85 to 90%, is dark matter, invisible and mysterious. And so we learned by 1940s to 1950s astronomers established basic Milky Way structure, spiral galaxy with our sun and disk far from center. But profound question remained: what was at center itself? Galactic core located in Sagittarius direction was hidden behind vast interstellar dust clouds blocking visible light. Looking toward galactic center with optical telescope was like trying to see through thick fog. Dust absorbed and scattered distant starlight, leaving our galaxy's heart shrouded in darkness. We discovered breakthrough came with radio astronomy development. Radio waves, unlike visible light, can pass through interstellar dust almost unimpeded. In 1950s to 1960s, astronomers using radio telescopes began mapping galactic center and discovered something extraordinary: intense radio emission source right at Milky Way center, compact regions seeming to mark galaxy's exact gravitational heart. This source, named Sagittarius A, SGRA for short, would become one of astronomy's most studied objects. We found as radio astronomy techniques improved, astronomers refined SGRA observations, discovering it actually consisted of several components. Most interesting was very compact bright radio source called Sagittarius A*, pronounced Sagittarius A star, tiny region no larger than Mercury's orbit emitting tremendous energy amounts. What could possibly produce such intense radiation from such small space? Answer: astronomers began suspecting something predicted by Einstein's general relativity theory but never definitively observed: a black hole. We learned by 1990s to 2000s astronomers developed powerful infrared telescopes that, like radio telescopes, could peer through dust to see galactic center. Using these instruments began tracking individual star motions orbiting very close to SGRA*, found astonishing. These stars moving at incredible speeds, thousands of kilometers per second, whipping around SGRA* in tight elliptical orbits. One star designated S2 completes full SGRA* orbit in just 16 years, despite its orbit taking it billions of miles from center. We discovered by applying Newton's and Einstein's gravity laws to these stellar orbits, astronomers could calculate central object mass pulling on these stars. Results staggering. Sagittarius A** contains approximately 4 million times Sun's mass, all compressed into regions smaller than Mercury's orbit. Only one explanation could account for so much mass in such small space. Sagittarius A** is supermassive black hole sitting at Milky Way galaxy's very center. We found this discovery revealed our galaxy as monster lurking at its heart, black hole so massive that if active and feeding on nearby matter would shine brighter than billions of stars combined. Fortunately for us, SGRA*, currently relatively quiet, not actively consuming large material amounts, so doesn't blaze with intense radiation characterizing active galactic nuclei in other galaxies. But it's there, invisible gravitational anchor holding galaxy's central region in its grip, Reminder: even most beautiful cosmic structures can harbor violent extreme objects at cores. We learned supermassive black hole presence raised new questions. How did it form? Was it there from galaxy history's very beginning, or did it grow over time? Most intriguingly, nearly every large galaxy astronomers observe seems to have supermassive black hole at its center. Our neighboring Andromeda galaxy is one too, even more massive than ours, perhaps 100 million times Sun's mass, suggested deep connection between galaxies and their central black holes, relationship astronomers still working to understand fully. We discovered while astronomers uncovering galactic center secrets, others studying how Milky Way moves. Our Sun, along with all other neighborhood stars traveling through space at about 514,000 miles per hour, roughly 230 kilometers per second, in roughly circular orbit around galactic center. At this speed takes Sun approximately 225 to 250 million years to complete one full orbit, period sometimes called galactic year or cosmic year. We found this means since Sun formed about 4.6 billion years ago, has completed roughly 20 galactic orbits. Last time Sun was at this orbital point, one cosmic year ago, about 225 million years ago, dinosaurs had just begun appearing on Earth. Time before that, about 450 million years ago, first fish were evolving in Earth's oceans. Every Earth history point, every life evolution moment, occurred during Sun's slow, patient Milky Way journey, riding galactic currents through space. We learned this orbital motion revealed another mystery with profound universe understanding implications. When astronomers measured star and gas orbital speeds at different galactic center distances, found something unexpected, same puzzle from discussing why everything spins. Based on visible galaxy matter, stars and glowing gas we can see, outer region stars should be orbiting more slowly than those closer to center, just as outer planets orbit more slowly than inner planets. We discovered, but that's not what they found. Instead, Milky Way rotation curve was flat, outer reach stars moving just as fast as those closer in, sometimes even faster. This meant not enough visible matter to account for gravitational pull needed to keep these stars in orbits. They should be flying off into intergalactic space, flung away by own speed, yet they weren't. Something holding galaxy together, providing extra gravity needed to keep outer stars galaxy-bound. We found this something was dark matter, mysterious invisible substance not emitting, absorbing, or reflecting light, but whose gravitational influence detectable through effects on visible matter. Milky Way, like all galaxies, embedded in vast dark matter halo extending far beyond visible star disk. Dark matter halo provides gravitational scaffolding holding galaxy together, explaining flat rotation curve. In fact, dark matter halo far more massive than all galaxies' visible matter combined, stars, gas, dust we can see. Everything making Milky Way visible and beautiful, represents only about 10 to 15% of galaxies' total mass. Rest about 85 to 90% is dark matter, invisible and mysterious. Each fact a gentle reminder of how the Milky Way reveals itself through patient observation, from radio waves penetrating dust to infrared light tracking orbiting stars, from measuring galactic rotation to discovering invisible dark matter. At our galaxy's heart sits a supermassive black hole, quiet now but massive beyond comprehension, and surrounding everything is a halo of mysterious matter we cannot see but know must be there. Rest in this cosmic mystery now, this recognition that most of what holds our galaxy together is invisible to us, that we live in a galaxy anchored by a black hole and embedded in dark matter. There's profound peace in accepting that the universe holds secrets we're only beginning to glimpse, that mystery and knowledge walk hand in hand. Let yourself drift with the sun's slow orbit around the galactic center, carried along at 500,000 miles per hour yet feeling perfectly still, held in place by gravity both visible and invisible, peaceful and unhurried, moving gently towards sleep. As we continue our peaceful journey through the story of the Milky Way, we move from understanding the galaxy's present structure to exploring its past and future, how it came to be, what it's made of, and the slow cosmic dance it performs with its neighboring galaxies. The Milky Way is not static or eternal but rather a living, evolving structure with a birth, a history, and an eventual fate written in the laws of gravity and motion. The question of how the Milky Way formed takes us back to the very beginning, not quite to the Big Bang itself, but to the cosmic dark ages that followed it, a time about 13.8 billion years ago when the universe was very different from today. In those early times, just a few 100 million years after the Big Bang, the universe was filled with vast clouds of hydrogen and helium gas, the simplest elements created in the Big Bang's aftermath. These clouds were not distributed uniformly but had slight variations in density, small ripples in the cosmic fabric left over from quantum fluctuations in the infant universe. These density variations, though tiny, were enough. Gravity, patient and inexorable, began to amplify them. Regions that were slightly denser than average attracted more matter, becoming even denser. Over millions of years, these overdense regions pulled in more and more gas, growing larger and more massive. The dark matter, which dominated the mass of these regions, collapsed first, creating gravitational wells into which the normal matter, the hydrogen and helium gas, could fall. These collapsing clouds of gas and dark matter were the seeds from which galaxies would grow. The Milky Way began as one of these collapsing clouds, probably about 13 billion years ago or slightly less. As the gas fell inward under gravity's pull, it began to rotate, just as we discussed when exploring why everything spins. The cloud inherited angular momentum from the turbulent motions of the early universe. This rotation caused the collapsing gas to flatten into a disk, the same process that created the solar system's disk billions of years later. Within this disk in the denser central regions, the gas became dense and hot enough for the first stars to ignite, beginning the Milky Way's long stellar history. But galaxy formation wasn't a smooth, simple process. The early Milky Way was a chaotic, violent place. Small proto-galaxies, dwarf galaxies and star clusters, were constantly merging together, colliding and combining to build larger structures. Each merger brought new gas to fuel star formation and added to the growing mass of the Milky Way. The oldest stars in our galaxy, found primarily in the spherical halo and in globular clusters, are relics of this early epoch, some nearly as old as the universe itself, 13 billion years or more. These ancient stars are metal poor, meaning they contain very little of any element heavier than helium, because they formed before generations of stars had lived and died to enrich the galaxy with heavier elements. Evidence for this violent early history can be found by studying the motions and compositions of stars throughout the Milky Way. In 2018, data from the Gaia spacecraft, the European mission precisely measuring the positions and motions of over 1 billion stars, revealed something remarkable. Astronomers discovered a population of stars in the Milky Way's halo that all moved in a similar unusual way, distinct from the general rotation of the galaxy. By analyzing these stars' motions and ages, astronomers concluded they were the remnants of a dwarf galaxy that had collided with the Milky Way about 10 billion years ago. This ancient dwarf galaxy, which astronomers named Gaia Enceladus, was torn apart by the Milky Way's gravity during the collision. Its stars were scattered and now orbit in the halo, a ghostly reminder of a merger that happened when the universe was less than a quarter of its current age. This discovery confirmed what simulations had long suggested: the Milky Way grew by consuming smaller galaxies, building itself up through countless mergers over billions of years. Our galaxy is, in a sense, a cosmic graveyard, filled with the scattered remains of galaxies that fell into its gravitational embrace eons ago. The disk of the Milky Way, the flat spiral structure where our Sun resides, formed later, perhaps 10 to 12 billion years ago, after much of the violent early merging had subsided. Gas that had settled into a rotating disk began forming stars in a more orderly fashion, creating the thin disk that contains most of the galaxy's visible stars today. But star formation in the Milky Way didn't happen all at once. It's been ongoing for billions of years, with new generations of stars continually being born from clouds of gas and dust. Each generation of stars has enriched the galaxy with heavier elements, what astronomers call metals, which includes everything heavier than hydrogen and helium. When massive stars die in supernova explosions, they scatter these heavy elements, carbon, oxygen, iron, and all the other elements of the periodic table, into space. These elements mix with the interstellar gas and are incorporated into the next generation of stars and planets. The Sun, which formed about 4.6 billion years ago, is a relatively metal-rich star compared to the galaxy's oldest stars, because it formed from gas that had been enriched by billions of years of stellar evolution. This means that the atoms in your body, the carbon in your DNA, the calcium in your bones, the iron in your blood, were created in the nuclear furnaces of stars that lived and died before the Sun was born. These stars exploded as supernovae, scattering their heavy elements into space, and eventually some of that enriched material collected into the cloud of gas and dust that collapsed to form the solar system. You are made of stardust in the most literal sense, forged in stellar cores and dispersed through the Milky Way over billions of years before eventually becoming part of you. The Milky Way continues to form stars today, though at a more leisurely pace than in its youth. Astronomers estimate that the galaxy creates roughly 1 to 2 new stars per year from the gas and dust that remains in the galactic disk. This might not sound like much, but over millions of years it adds up. The star formation occurs primarily in the spiral arms, where gas clouds are compressed by density waves and gravitational interactions, triggering the collapse of clouds into new star clusters. When you see bright, blue regions in images of spiral galaxies, you're seeing these stellar nurseries, regions where massive young stars are being born and lighting up their surroundings. But the Milky Way is not a closed system. It continues to interact with its environment, with the small satellite galaxies that orbit it, and most dramatically, with its neighboring large galaxy, Andromeda. The Andromeda Galaxy, also called M31, is the closest large spiral galaxy to the Milky Way, about 2.5 million light-years away. On a dark night far from city lights, you can see Andromeda with the naked eye as a faint, fuzzy patch in the constellation Andromeda. It appears small and unimpressive to the eye, but that tiny smudge contains 1 trillion stars, roughly twice as many as our Milky Way. And Andromeda is moving toward us. Astronomers discovered in the early 20th century, using the same techniques that Hubble employed to measure galaxy distances, that Andromeda is approaching the Milky Way at about 110 kilometers per second, roughly 250,000 miles per hour. This is unusual. Most galaxies in the universe are moving away from us due to the expansion of space, showing redshifts in their light. But Andromeda shows a blue shift, indicating it's moving toward us. The reason is gravity. The Milky Way and Andromeda are close enough that their mutual gravitational attraction overcomes the expansion of the universe, pulling them together. This discovery raised an inevitable question: will the Milky Way and Andromeda collide? The answer, worked out through careful measurements and computer simulations, is yes. In approximately 4.5 billion years, the Milky Way and Andromeda will begin to merge. This will be a slow-motion collision taking hundreds of millions of years to complete. As the two galaxies approach each other, their gravity will distort their shapes, pulling out long streams of stars called tidal tails. When they finally interpenetrate, their spiral structures will be disrupted. Their gas clouds will collide and trigger enormous bursts of star formation, and their supermassive central black holes will eventually spiral together and merge. And so we learned the question of how Milky Way formed takes us back to very beginning, about 13.8 billion years ago, when universe very different from today. In those early times, just few hundred million years after Big Bang, universe filled with vast hydrogen and helium gas clouds, simplest elements created in Big Bang's aftermath, clouds not uniformly distributed but had slight density variations, small cosmic fabric ripples left over from quantum fluctuations in infant universe. We discovered these density variations, though tiny, were enough. Gravity, patient and inexorable, began amplifying them. Regions slightly denser than average attracted more matter, becoming even denser. Over millions of years, overdense regions pulled in more and more gas, growing larger and more massive. Dark matter dominating these regions, mass collapsed first, creating gravitational wells into which normal matter, hydrogen and helium gas, could fall. These collapsing gas and dark matter clouds were seeds from which galaxies would grow. We found Milky Way began as one of these collapsing clouds, probably about 13 billion years ago or slightly less. As gas fell inward under gravity's pull, began to rotate, cloud inherited angular momentum from early universe turbulent motions. Rotation caused collapsing gas to flatten into disk, same process creating solar system disk billions of years later. Within this disk and denser central regions, gas became dense and hot enough for first stars to ignite, beginning Milky Way's long stellar history. We learned galaxy formation wasn't smooth, simple process. Early Milky Way was chaotic, violent place. Small proto-galaxies, dwarf galaxies and star clusters, constantly merging together, colliding and combining to build larger structures. Each merger brought new gas to fuel star formation and added to growing Milky Way mass. Galaxies' oldest stars, found primarily in spherical halo and globular clusters, are relics of this early epoch, some nearly as old as universe itself, 13 billion years or more. These ancient stars are metal poor, contain very little of any element heavier than helium, because formed before generations of stars lived and died to enrich galaxy with heavier elements. We discovered evidence for violent early history found by studying star motions and compositions throughout Milky Way. In 2018, data from Gaia spacecraft, European mission precisely measuring over a billion star positions and motions, revealed something remarkable. Astronomers discovered Milky Way halo star population all moving in similar unusual way, distinct from general galaxy rotation. Analyzing these stars' motions and ages, astronomers concluded they were remnants of dwarf galaxy that collided with Milky Way about 10 billion years ago. We found this ancient dwarf galaxy astronomers named Gaia Enceladus was torn apart by Milky Way's gravity during collision, its stars scattered and now orbit in halo, ghostly reminder of merger when universe was less than quarter current age. Discovery confirmed what simulations long suggested. Milky Way grew by consuming smaller galaxies, building itself up through countless mergers over billions of years. Our galaxy is in sense cosmic graveyard filled with scattered remains of galaxies that fell into its gravitational embrace eons ago. We learned Milky Way disk, flat spiral structure where our sun resides, formed later, perhaps 10 to 12 billion years ago after much violent early merging subsided. Gas that settled into rotating disk began forming stars in more orderly fashion, creating thin disk containing most galaxies' visible stars today. But star formation in Milky Way didn't happen all at once, ongoing for billions of years with new star generations continually being born from gas and dust clouds. We discovered each star generation has enriched galaxy with heavier elements, what astronomers call metals, everything heavier than hydrogen and helium. When massive stars die in supernova explosions scatter these heavy elements, carbon, oxygen, iron, all periodic table elements, into space. Elements mix with interstellar gas and incorporate into next generation stars and planets. Sun, which formed about 4.6 billion years ago, is relatively metal-rich star compared to galaxy's oldest stars because formed from gas enriched by billions of years stellar evolution. We found this means atoms in your body, carbon in DNA, calcium in bones, iron in blood, were created in nuclear furnaces of stars that lived and died before Sun was born. These stars exploded as supernovae scattering heavy elements into space. Eventually some enriched material collected into gas and dust cloud that collapsed, forming solar system. You are made of stardust in most literal sense, forged in stellar cores and dispersed through Milky Way over billions of years before eventually becoming part of you. We learned Milky Way continues forming stars today, though at more leisurely pace than in youth. Astronomers estimate galaxy creates roughly 1 to 2 new stars per year from gas and dust remaining in galactic disk. Might not sound like much, but over millions of years adds up. Star formation occurs primarily in spiral arms where gas clouds compressed by density waves and gravitational interactions triggering cloud collapse into new star clusters. Bright blue regions and spiral galaxy images are these stellar nurseries, regions where massive young stars being born and lighting up surroundings. We discovered Milky Way is not closed system, continues interacting with environment, with small satellite galaxies orbiting it, and most dramatically with neighboring large galaxy Andromeda. Andromeda Galaxy, also called M31, is closest large spiral galaxy to Milky Way, about 2.5 million light-years away. On dark night far from city lights can see Andromeda with naked eye as faint fuzzy patch, and Andromeda constellation appears small and unimpressive, but that tiny smudge contains trillion stars, roughly twice as many as our Milky Way. We found Andromeda moving toward us. Astronomers discovered early 20th century using same techniques Hubble employed for galaxy distances that Andromeda approaching Milky Way at about 110 kilometers per second, roughly 250,000 miles per hour. This unusual, most universe galaxies moving away from us due to space expansion showing redshifts in light, but Andromeda shows blue shift indicating moving toward us. Reason is gravity. Milky Way and Andromeda close enough that mutual gravitational attraction overcomes universe expansion pulling them together. We learned this discovery raised an inevitable question: will Milky Way and Andromeda collide? Answer worked out through careful measurements and computer simulations is yes. In approximately 4.5 billion years, Milky Way and Andromeda will begin to merge. This will be slow-motion collision taking hundreds of millions of years to complete. As two galaxies approach each other, their gravity will distort shapes, pulling out long star streams called tidal tails. When finally interpenetrate, their spiral structures will be disrupted. Gas clouds will collide, triggering enormous star formation bursts, and supermassive central black holes will eventually spiral together and merge. Each fact a gentle reminder that the Milky Way has a story, a birth from collapsing gas clouds, a violent youth of mergers and collisions, a gradual enrichment through generations of stars, and an eventual fate merging with Andromeda. We are temporary residents in this evolving structure, made of atoms created in previous generations of stars, witnesses to one brief moment in the galaxy's long history. Rest in this cosmic perspective now, this recognition that the galaxy is not eternal but evolving, that it formed from chaos and will eventually merge into something new. You are made of the Milky Way's history, forged in stars long dead, part of the ongoing story written in starlight. Let yourself drift with this ancient galaxy's slow evolution, this patient transformation unfolding over billions of years, peaceful and unhurried, carried gently towards sleep. As we continue our peaceful journey through the story of the Milky Way, we turn to the galaxy's companions, the smaller satellite galaxies that orbit it like moons around a planet, and to the larger cosmic neighborhood in which the Milky Way resides. Our galaxy does not drift alone through the cosmos but rather exists as part of a complex hierarchy of structures, from the smallest dwarf galaxies to the vast cosmic web that stretches across the entire observable universe. The Milky Way is not solitary. Orbiting around it, caught in its gravitational embrace, are dozens of smaller satellite galaxies. These range from tiny dwarf galaxies containing just a few thousand stars to larger companions like the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere as fuzzy patches of light that early explorers thought were detached pieces of the Milky Way itself. The Magellanic Clouds were named after Ferdinand Magellan, whose crew observed them during the first circumnavigation of Earth in the early 1500s, though indigenous peoples of the southern hemisphere had known about them for thousands of years. The Large Magellanic Cloud, or LMC, is the brightest satellite galaxy of the Milky Way, containing about 30 billion stars, substantial compared to the smallest dwarf galaxies but still just a fraction of the Milky Way's stellar population. It orbits the Milky Way at a distance of about 160,000 light-years, which is relatively close in cosmic terms, roughly the diameter of the Milky Way's own disk. The Small Magellanic Cloud, or SMC, is smaller and slightly more distant, containing perhaps 3 billion stars and orbiting at about 200,000 light-years. These two galaxies are gravitationally bound to each other as well as to the Milky Way, and they're slowly spiraling inward, eventually destined to be torn apart and absorbed by our galaxy's gravity over billions of years. The Magellanic Clouds are scientifically precious because they're close enough that we can study individual stars within them, yet far enough that we can see them from the outside and understand their overall structure, something we can't do for the Milky Way itself since we're embedded within it. Astronomers have used the Magellanic Clouds as laboratories for studying stellar evolution, measuring cosmic distances. Remember, Henrietta Leavitt's Cepheid variables were in the small Magellanic Cloud, and understanding how galaxies interact. In 1987, a star in the Large Magellanic Cloud exploded as a supernova, supernova 1987A, the closest supernova visible to the naked eye since Kepler's supernova in 1604, providing astronomers with an unprecedented opportunity to study a stellar explosion in detail. Beyond the Magellanic Clouds, the Milky Way has many other satellite galaxies, most of them much smaller and fainter. Some, like the Sagittarius dwarf elliptical galaxy, are so faint and diffuse that they were only discovered in recent decades despite being relatively close. Sagittarius dwarf is on the opposite side of the galactic center from us, only about 70,000 light-years away, but it's so scattered and dim that it wasn't found until 1994. This galaxy is currently being torn apart by the Milky Way's tidal forces, stretched into long streams of stars wrapping around our galaxy, another example of the ongoing cannibalism that has characterized the Milky Way's growth. Astronomers continue to discover new satellite galaxies as telescope technology improves. Many of these are ultra-faint dwarf galaxies containing only a few thousand stars, so dim that they're invisible to all but the most sensitive surveys. These tiny galaxies are interesting not just as curiosities but because they may help solve one of the Milky Way's mysteries. Computer simulations of galaxy formation predict that galaxies like the Milky Way should have hundreds or even thousands of satellite galaxies, far more than the few dozen we've actually found. This is called the missing satellites problem, and it's still not entirely resolved. Perhaps the missing satellites are there but too faint to detect, or perhaps our understanding of dark matter and galaxy formation needs refinement. The Milky Way and its satellites are part of a larger structure called the Local Group, a collection of more than 80 galaxies bound together by gravity, occupying a region of space about 10 million light-years across. The Local Group is dominated by two large spiral galaxies, the Milky Way and Andromeda. These two giants contain most of the mass and most of the stars in the Local Group. The third largest member is Triangulum, or M33, a smaller spiral galaxy about 3 million light-years away that contains perhaps 40 billion stars. All the other members of the Local Group are dwarf galaxies, either orbiting the Milky Way or Andromeda, or drifting in the spaces between. The Local Group itself is not isolated but sits on the outskirts of an even larger structure called the Virgo supercluster, also known as the Local Supercluster. This is an immense collection of galaxy groups and clusters, containing tens of thousands of galaxies spread across a region about 110 million light-years in diameter. At the heart of the Virgo supercluster is the Virgo cluster, a dense concentration of about 1,500 galaxies located about 65 million light-years from us. The gravity of this massive cluster influences everything around it, including our Local Group, which is slowly falling toward the Virgo cluster, pulled by its immense gravitational attraction. But even the Virgo supercluster is just one feature in an even grander structure. In recent years, astronomers mapping the large-scale distribution of galaxies across the cosmos have discovered that we're part of an enormous structure called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, containing about 100,000 galaxies including the Virgo supercluster and many neighboring structures, all connected by flows of galaxies moving through space under the influence of gravity. The Milky Way sits on the outer edge of Laniakea, about 500 million light-years from its center. These enormous structures, superclusters like Laniakea, are arranged in a cosmic web, with long filaments of galaxies separated by vast voids containing very few galaxies. If you could step back and see the distribution of galaxies across billions of light-years, you would see a pattern like a three-dimensional spider web, with dense filaments and walls of galaxies surrounding enormous empty bubbles. This cosmic web is the largest scale structure in the universe, shaped by the distribution of dark matter in the moments after the Big Bang and evolved over billions of years through gravitational collapse. Within this vast cosmic context, the Milky Way is simultaneously insignificant and precious. It's one galaxy among hundreds of billions, sitting on the edge of one supercluster among countless superclusters, a tiny eddy in the cosmic web. Yet it's also the only galaxy we can study in intimate detail, the only one we can map star by star, the only one we know contains life. Every fact we've learned about the Milky Way, from its supermassive black hole to its dark matter halo, from its ancient stars to its ongoing star formation, from its past mergers to its future collision with Andromeda, tells us something not just about our home galaxy but about how all galaxies form, evolve, and interact across cosmic time. The Milky Way is also a time machine of sorts. Because light takes time to travel, when we look at distant parts of the galaxy, we're seeing them as they were in the past. The galactic center, 26,000 light-years away, appears to us as it was 26,000 years ago, before human civilization, before agriculture, when our ancestors were hunter-gatherers painting caves in Europe. Stars on the far side of the galaxy appear as they were 50,000 or 100,000 years ago. And when we look at the Magellanic Clouds or Andromeda, we're seeing them as they were hundreds of thousands or millions of years in the past. And so we learn the Milky Way is not solitary. Orbiting around it, caught in its gravitational embrace, are dozens of smaller satellite galaxies. These range from tiny dwarf galaxies containing just few thousand stars to larger companions like large and small Magellanic Clouds visible to naked eye from southern hemisphere as fuzzy light patches early explorers thought were detached Milky Way pieces. Magellanic Clouds named after Ferdinand Magellan, whose crew observed them during early 1500s first Earth circumnavigation, though indigenous Southern Hemisphere peoples known about them for thousands of years. We discovered Large Magellanic Cloud, LMC, is Milky Way's brightest satellite galaxy containing about 30 billion stars, substantial compared to smallest dwarf galaxies but still just fraction of Milky Way's stellar population. Orbits Milky Way at about 160,000 light-years distance, relatively close in cosmic terms, roughly Milky Way's own disk diameter. Small Magellanic Cloud, SMC, smaller and slightly more distant, containing perhaps 3 billion stars orbiting at about 200,000 light-years. These two galaxies gravitationally bound to each other into Milky Way, slowly spiraling inward, eventually destined to be torn apart and absorbed by our galaxy's gravity over billions of years. We found Magellanic Clouds scientifically precious because close enough to study individual stars within them, yet far enough to see from outside and understand overall structure, something can't do for Milky Way since we're embedded within it. Astronomers used Magellanic Clouds as laboratories for studying stellar evolution, measuring cosmic distances. Remember, Henrietta Leavitt's Cepheid variables were in small Magellanic Cloud, understanding how galaxies interact. In 1987, a large Magellanic Cloud star exploded as supernova, supernova 1987A, closest naked eye visible supernova since Kepler's supernova in 1604. Providing astronomers unprecedented opportunity to study stellar explosion in detail. We learned beyond Magellanic Clouds, Milky Way has many other satellite galaxies, most much smaller and fainter. Some, like Sagittarius, dwarf elliptical galaxies so faint and diffuse, only discovered in recent decades. Despite being relatively close, Sagittarius dwarf is on opposite galactic center side from us, only about 70,000 light-years away, but so scattered and dim wasn't found until 1994. This galaxy, currently being torn apart by Milky Way's tidal forces, stretched into long star streams wrapping around our galaxy, another ongoing cannibalism example characterizing Milky Way's growth. We discovered astronomers continue discovering new satellite galaxies as telescope technology improves. Many are ultra-faint dwarf galaxies containing only few thousand stars, so dim and visible to all but most sensitive surveys. These tiny galaxies interesting not just as curiosities but may help solve Milky Way mysteries. Computer simulations of galaxy formation predict galaxies like Milky Way should have hundreds or even thousands of satellite galaxies, far more than few dozen actually found, called missing satellites problem, still not entirely resolved. Perhaps missing satellites there but too faint to detect, or perhaps our dark matter and galaxy formation understanding needs refinement. We found Milky Way and its satellites are part of larger structure called local group, collection of more than 80 galaxies bound together by gravity occupying region about 10 million light-years across. Local group dominated by two large spiral galaxies, Milky Way and Andromeda. These two giants contain most mass and most stars in local group. Third largest member is Triangulum, M33, smaller spiral galaxy about 3 million light-years away containing perhaps 40 billion stars. All other local group members are dwarf galaxies either orbiting Milky Way or Andromeda or drifting in spaces between. We learned local group itself not isolated but sits on outskirts of even larger structure called Virgo supercluster, also known as local supercluster, immense collection of galaxy groups and clusters containing tens of thousands of galaxies spread across region about 110 million light-years diameter. At Virgo supercluster heart is Virgo cluster, dense concentration of about 1,500 galaxies located about 65 million light-years from us. This massive cluster's gravity influences everything around it, including our local group, which is slowly falling toward Virgo cluster pulled by its immense gravitational attraction. We discovered even Virgo supercluster is just one feature in grander structure. Recent years astronomers mapping large-scale galaxy distribution across cosmos discovered we're part of enormous structure called Laniakea, Hawaiian word meaning immeasurable heaven. Laniakea is supercluster of superclusters containing about 100,000 galaxies including Virgo supercluster and many neighboring structures, all connected by galaxy flows moving through space under gravity's influence. Milky Way sits on Laniakea's outer edge about 500 million light-years from its center. We found these enormous structures, superclusters like Laniakea, arranged in cosmic web with long galaxy filaments separated by vast voids containing very few galaxies. If could step back and see galaxy distribution across billions of light-years, would see pattern like three-dimensional spider web with dense filaments and galaxy walls surrounding enormous empty bubbles. This cosmic web is universe's largest scale structure, shaped by dark matter distribution in moments after Big Bang and evolved over billions of years through gravitational collapse. We learned within this vast cosmic context, Milky Way is simultaneously insignificant and precious, one galaxy among hundreds of billions, sitting on one supercluster edge among countless superclusters, tiny eddy in cosmic web, yet also only galaxy we can study in intimate detail, only one we can map star by star, only one we know contains life. Every Milky Way fact learned, from supermassive black hole to dark matter halo, ancient stars to ongoing star formation, past mergers to future Andromeda collision, tells us something not just about home galaxy but about how all galaxies form, evolve, interact across cosmic time. We discovered Milky Way is also time machine of sorts, because light takes time to travel. When we look at distant galaxy parts, we're seeing them as they were in past. Galactic center 26,000 light-years away appears to us as it was 26,000 years ago, before human civilization, before agriculture, when our ancestors were hunter-gatherers painting European caves. Far-side stars appear as they were 50,000 or 100,000 years ago. When we look at Magellanic Clouds or Andromeda, we're seeing them as they were hundreds of thousands or millions of years in past. Each fact a gentle reminder of the Milky Way's place in the cosmos, not alone but surrounded by smaller companions, part of the local group, sitting in the Virgo supercluster, on the edge of Laniakea, embedded in the cosmic web. We are part of nested structures stretching from our solar system to the observable universe, each level revealing new patterns, new connections. Rest in this cosmic perspective now, this recognition that the Milky Way is both ordinary and unique, both insignificant and irreplaceable. We are tiny in the cosmic scheme, yet we are here, aware, contemplating our place in this vast hierarchy of structures. Let yourself drift with the Milky Way through its cosmic neighborhood, surrounded by satellite galaxies, falling slowly toward the Virgo cluster, part of Laniakea's immeasurable heaven, peaceful and unhurried, carried gently towards sleep. As we approach the end of our peaceful journey through the story of the Milky Way, we turn to the final questions: what the future holds for our galaxy, how we continue to explore it with new technologies, and what it means to be conscious beings living within this vast spiral of stars, aware of our cosmic home in ways that no previous generation could have imagined. The collision between the Milky Way and Andromeda that we discussed earlier, that cosmic encounter scheduled for about 4.5 billion years from now, will be the defining event in our galaxy's future. But what will this merger actually look like, and what will be the result? Computer simulations, growing more sophisticated with each passing year, have given astronomers detailed predictions about how this slow-motion collision will unfold. The process will be beautiful and violent, a cosmic dance played out over hundreds of millions of years. As the two galaxies approach each other, their shapes will begin to distort. Gravity doesn't pull uniformly, the side of each galaxy facing the other will feel stronger gravitational attraction than the far side, creating tidal forces that will stretch both galaxies into elongated shapes. Long streamers of stars, called tidal tails, will be pulled out from both galaxies, creating bridges and arcs of stars stretching across millions of light-years of space. These tidal tails will be spectacular, visible across vast distances, evidence of two giant galaxies in the throes of merger. The first close passage between the Milky Way and Andromeda will be dramatic but not final. The two galaxies will interpenetrate, passing through each other, their stars intermingling but almost never actually colliding. Space between stars is so vast that stellar collisions will be extraordinarily rare even during the merger. But the gas clouds within each galaxy will collide, and these collisions will compress the gas, triggering enormous bursts of star formation. Regions that had been quiescent for billions of years will suddenly blaze with the light of millions of newly forming stars, creating brilliant blue regions visible across intergalactic distances. After this first passage, the two galaxies will swing past each other, pulled apart by their momentum but still bound by gravity. They'll move apart for perhaps hundreds of millions of years before falling back together for a second passage, then a third, each time losing orbital energy through gravitational interactions. Eventually, perhaps a billion years after the first contact, the two galaxies will settle into a single merged structure. The elegant spiral patterns of both galaxies will be destroyed in this process, their disks disrupted and their spiral arms unwound. The result will be a giant elliptical galaxy, a smooth football-shaped swarm of stars with no distinct spiral structure, no well-defined disk. Astronomers have already given this future merged galaxy a name, Milkomeda, a blend of Milky Way and Andromeda. Milkomeda will be one of the largest galaxies in the local group, containing over 1 trillion stars, all the stars from both the Milky Way and Andromeda, plus new stars formed during the merger process. At its center will be a single supermassive black hole, the result of the merger between the Milky Way's 4 million solar mass black hole and Andromeda's 100 million solar mass black hole. This merged black hole will be truly enormous, perhaps 110 million times the mass of the Sun. But will anyone, or anything, be around to witness this spectacle? The merger will occur about 4.5 billion years from now. By that time, the Sun will be approaching the end of its life. Our Sun, like all stars, has a finite lifetime determined by how long its nuclear fuel will last. The Sun has been burning hydrogen in its core for about 4.6 billion years, converting it to helium through nuclear fusion, releasing the energy that makes the Sun shine and makes life on Earth possible. But this process cannot continue forever. In about 5 billion years, the Sun will exhaust the hydrogen in its core. When this happens, the core will contract and heat up, while the outer layers will expand dramatically. The Sun will become a red giant star, growing so large that it will engulf Mercury and Venus and possibly even Earth. The Earth's oceans will boil away, its atmosphere will be stripped, and our planet will become uninhabitable long before the Sun actually engulfs it, perhaps in as little as 1 billion years. Increasing solar luminosity will make Earth's surface too hot for liquid water to exist. So the fate of life on Earth is intimately tied to the evolution of the Sun, and that evolution is inexorable. This might sound bleak, but it's important to remember the timescales involved. 1 billion years is an almost inconceivably long time. Life has existed on Earth for about 3.8 billion years. 1 billion years ago, the most complex life forms were simple multicellular organisms. The entire evolution from simple ocean life to humans has happened in less than 1 billion years. What might life, or intelligence, become in the billion years remaining before Earth becomes uninhabitable? We cannot know, but the possibilities are limitless. And perhaps by then, if intelligence survives and continues to develop, our descendants, whether biological or artificial, might have spread beyond Earth, beyond the solar system, to other stars in the Milky Way. The galaxy contains hundreds of billions of stars, and we now know that planets are common. Nearly every star has at least one planet, and many have multiple planets. Some unknown fraction of these planets will be in their star's habitable zone, where conditions might be right for life. The Milky Way might already be teeming with life, with countless worlds hosting their own biospheres, their own evolutionary experiments. Or we might be alone, or nearly alone, one of the first species in the galaxy to develop technology and contemplate the cosmos. This is the Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody?" If intelligent life is common, why haven't we detected any signs of it? Why don't we see evidence of advanced civilizations, megastructures around stars, radio signals, probes visiting our solar system? The silence is puzzling and has led to many proposed explanations, from the optimistic, intelligent civilizations are common but avoid contacting us, to the sobering, intelligent civilizations inevitably destroy themselves or face insurmountable barriers to expansion. We don't know the answer to Fermi's question, and we may not know for a long time. But we continue to search, to listen, to explore. Our understanding of the Milky Way has been transformed in recent years by new observational technologies. The Gaia spacecraft, launched by the European Space Agency in 2013, has measured the positions and motions of over 1.8 billion stars with unprecedented precision, creating the most detailed three-dimensional map of the Milky Way ever made. This data has revolutionized our understanding of the galaxy's structure, dynamics, and history, revealing streams from disrupted satellites, mapping the spiral arms in new detail, and even detecting the subtle wobbles and stellar motions caused by the gravity of unseen planets. Radio telescopes, infrared telescopes, X-ray telescopes, each seeing the Milky Way in different wavelengths of light, have revealed phenomena invisible to our eyes. We can now map the distribution of hydrogen gas throughout the galaxy using radio waves, trace the paths of high-energy particles around the supermassive black hole using X-rays, and peer through dust to see star formation in action using infrared light. Every new wavelength observed, every new technology deployed, reveals the Milky Way in a new way, adding layers to our understanding. And we're not just passive observers anymore. Since the launch of Voyager 1 and Voyager 2 in the 1970s, we've sent spacecraft beyond the edge of the solar system into interstellar space, into the space between stars within the Milky Way. These spacecraft carry golden records with sounds and images from Earth, messages in a bottle for any civilization that might find them in the distant future as they drift through the galaxy. They're traveling slowly by cosmic standards. It will take tens of thousands of years for them to approach even the nearest stars, but they're moving, carrying a piece of humanity into the galactic expanse. Future missions may go farther and faster, concepts exist for laser-pushed light sails that could accelerate tiny probes to a significant fraction of the speed of light, allowing them to reach nearby stars in decades rather than millennia. Such probes could explore the planets of Alpha Centauri, our nearest stellar neighbor just 4.3 light-years away, and send back images and data. They would be the first time humanity, or any Earth life, had directly explored beyond our solar system, touching another part of the Milky Way. And so our journey through the Milky Way comes to its end, though the galaxy's story continues, unfolding over billions of years past and billions of years future. We've traveled from ancient myths to modern cosmology, from Galileo's first glimpse of countless stars to spacecraft mapping billions of stars in 3 dimensions. We've learned that the Milky Way is a spiral galaxy 100,000 light-years across, containing hundreds of billions of stars, with our Sun positioned in a minor spiral arm about 26,000 light-years from the center. We've discovered that at the galactic heart lies a supermassive black hole 4 million times the Sun's mass, and that the entire galaxy is embedded in a vast halo of dark matter far more massive than all the visible matter combined. We've learned that the Milky Way formed about 13 billion years ago from collapsing clouds of gas and dark matter, that it grew through mergers with smaller galaxies, and that it continues to cannibalize satellite galaxies even today. We've seen that the Milky Way is part of the local group of galaxies, dominated by the Milky Way and Andromeda, which are destined to merge in about 4.5 billion years to form a giant elliptical galaxy called Milkomeda. We've learned that the local group sits in the Virgo supercluster, on the edge of the enormous Laniakea supercluster, all part of the cosmic web that stretches across the observable universe. We've understood that we are made of the Milky Way in the most literal sense. The atoms in our bodies were created in stars that lived and died before the Sun was born, scattered through the galaxy by supernova explosions, eventually incorporated into the cloud that formed our solar system. We are stardust, arranged in such a way that we can contemplate our own origins, conscious pieces of the galaxy aware of the whole. As you rest now, know that you are part of this grand structure, this magnificent spiral of stars wheeling through space. The Milky Way is not something distant and separate from you, it is your home, your origin, your context. Every atom in your body has a cosmic history spanning billions of years. You are connected to the galaxy in the deepest possible way. And you are aware of this connection in a way that makes you precious. Somewhere in this galaxy of hundreds of billions of stars, on a small rocky planet orbiting an ordinary star in an unremarkable spiral arm, matter has become conscious. Atoms forged in stellar cores have assembled themselves into a form capable of understanding where they came from, capable of mapping the very galaxy that created them. This is extraordinary. This is miraculous, even if it arose through natural processes. You are the Milky Way looking at itself, understanding itself, wondering about itself. In you, the galaxy has become self-aware. This consciousness may be common in the universe, or it may be rare, we don't know yet. But here, now, in this moment, you carry that awareness. You are a way for the cosmos to know itself, as Carl Sagan once said. As you drift towards sleep, let yourself feel the weight of this cosmic connection. You are not separate from the universe, observing it from outside. You are part of it, made of it, a temporary pattern in the flow of matter and energy that has continued for billions of years and will continue for billions more. The Milky Way created you, and you have spent this time learning about the Milky Way. The circle is complete. The galaxy turns on, patient and eternal, completing one rotation every 225 million years, its stars slowly orbiting the central black hole, its spiral arms winding and unwinding through the action of density waves, its satellite galaxies orbiting in their slow dance, all of it moving through space as part of the larger cosmic web. And you turn with it, carried along at 514,000 miles per hour as the sun orbits the galactic center, though you feel perfectly still. You are in motion on every scale, spinning with Earth's rotation, orbiting the sun, circling the galaxy, falling toward the Virgo cluster, embedded in structures stretching hundreds of millions of light years. Yet here, now, you feel only stillness, only peace. This is the gift of our place in the cosmos. We are part of something vast and ancient and beautiful, yet we can rest in the immediate moment, in the here and now, held safely by forces we understand but cannot feel. You are held by Earth's gravity, carried by Earth's rotation, swept along by the sun's orbit, all of it so smooth and constant that it feels like perfect rest. Let go now. The Milky Way will continue its journey without your attention. The stars will keep burning, the galaxy will keep rotating, Andromeda will keep approaching, all on timescales so vast that your entire life is but a fleeting instant. And that's beautiful too. You are part of the eternal story, but you're also free from having to carry it. The cosmos takes care of itself. Sleep well, child of the Milky Way. You are home. You are safe. You are exactly where you belong, in this galaxy, on this planet, in this moment. The stars will be there tomorrow, wheeling overhead. The same light that has guided every human who has ever lived, the same galaxy that gave birth to the sun and the earth and you. Rest in the light of the Milky Way. Rest in the embrace of the galaxy. Rest. Good night.